Hey everyone! In this video, we'll explore some nuclear physics. Specifically, I was wondering about what the most stable isotopes are. In this video, we'll try to explore various factors for the stability of isotopes and then find out which isotopes are the most stable. Before we begin, we should explore our data as usual. In here, we'll be using isotope data. Let's take lead for example, and take its property known isotopes. This gives us the list of all isotopes of lead. As you can see, there's plenty of isotopes here. Elements on the periodic table are distinguished by their atomic number, which is the number of protons they have in their nucleus. However, alongside protons, atoms have neutrons in their nucleus as well. This varies by isotope. Isotopes are then just the same element but with different numbers of neutrons, which leads to different masses and stabilities. For a particular isotope, we also have several properties as seen here. One of these properties is whether the isotope is stable or not. So let's go ahead and group lead isotopes by their stability using the group by function. We see that only a few isotopes are actually stable, and most are not stable. Is this true for all elements? Let's explore this by counting stable and unstable isotopes. Using the entity value function, I will call the stability property for all isotopes and then use the counts function to tally up the states. As one can see, the overwhelming majority of isotopes are actually not stable. So, what does it take for an isotope to be stable? Well, there's a well-known region of stability. The reason some isotopes are unstable is that they do not stay with the same number of subatomic particles, that is neutrons, protons, or electrons, for a long time, and they decay radioactively into more stable atoms. Thus, it has been observed there's a happy region in the proportion of neutrons to protons that is particularly stable, which is called the band or belt of stability. Let's observe this. We'll make a list of lists in which there are three elements: neutron number, atomic number, and stability. I will use the entity value function applied to my isotope entity class to obtain this. I will also delete any missing stability values using my delete cases function. The underscores in the first two elements indicate that I want to delete patterns such that the first two elements are anything, but the third element has the head missing. Now I want to group pairs of neutron and proton numbers to their stability. This seems like a hard task, but the group by function makes it easy. The syntax here is that I am grouping my data by applying the most function and basing my grouping based on the last element, which is the stability. This way, I can get pairs of nucleon numbers associated with their stability. I can now use this data to visualize the belt of stability. Before we proceed though, what percentage is stable and what percentage is unstable? We didn't answer this question yet. Mapping the length function onto our data above and dividing by the length of our whole expression gives us that more than 90% of isotopes are not stable. Let's move on to visualizing this region of stability now. I am simply using a list plot here since it will take care of coloring in stability for me. It certainly seems like a solid linear correlation is present. I want to touch on another important idea: magic numbers. When atoms have these magic numbers as their proton or neutron numbers, they're usually very stable. For protons, these numbers are 2, 8, 20, 28, 50, 82, and 126, while only 126 is recognized for neutrons. Let's pick isotopes with those numbers in either their protons or neutrons. I will use the select function and contains any to detect any magic elements in my list, and will also set up an entity association. Now I will try to get the full symbols of all these isotopes and group them by stability. As usual, I will use the group by function and ensure that I am looking at the keys of my association. The only step to add here is mapping the entity value function onto my grouped association to get the full symbol of each isotope. As we can see, the elements helium, oxygen, calcium, nickel, tin, and lead are dominant in the stable category as their proton numbers are those magic numbers. Let's visualize this. Grouping my list again by stability and then using list plot, I can visualize stability or lack thereof. Now on to another exploration that I wondered about. Are even or odd numbers advantageous in stability? Let's find out. First, we'll start by looking at isotopes which are stable by taking all isotopes that are assigned to true in our grouped isotopes variable. We'll apply the odd_q function on this list and then group the outputs based on length. Through this, we are able to categorize isotopes into 4 groups, depending if the number of protons or the number of neutrons is odd or not, and for each group we can count the number of isotopes by mapping length. Based on this pie chart, it looks like even numbers are highly advantageous for stability. Most stable isotopes turn out to have an even number of nucleons. Odd numbers for both protons and neutrons seem particularly unfavorable. What about unstable isotopes? Is there a correlation there? Applying the same code to those isotopes assigned false in our data gives us a very balanced looking pie chart, so we can conclude from this that even numbers are advantageous for stability. Finally, let's hop into answering our question. We explored all these trends and factors in stability, but how can we get a direct solution to our problem? Binding energy per nucleon. This measurement basically signifies how strongly glued the nucleus is, which signifies its stability. We'll now construct some new data using the entity value function. For all isotopes, we'll set up an entity association between them and the list of both their mass numbers and binding energy per nucleon. We can look at a sample of this data by taking the first 2 elements using the span function. As always, let's visualize this data. We'll take the values in our data and plot the coordinates using listplot. As you can see though, for each mass number, there are multiple binding energies. So let's just take the maximum binding energy in each. I will do that using the group by function. What I'm basically doing is grouping binding energies by their mass number, which is the first element. The rest function here simply is my list with the first element removed, so it just is the second element or binding energy per nucleon. Finally, within each mass number grouping of binding energies, I will only take the maximum there. I can now plot this using the listplot function again, and as you can see, we have a peak around mass number 60. Now I'll take the largest 10 values from my data by using the takeLargestBy function and indicating that I want the largest 10 binding energies per nucleon, which is the last element. I get this list of elements, which look like they're all metals with mass numbers around 60. I can also get the most stable isotopes directly using entity class by indicating that I want to take the largest 10 entities in terms of binding energy per nucleon. This gives me the same output. Our most stable isotope has many of the same properties we talked about. It has an even number of both protons and neutrons, and its proton number is 28, which is a magic number. Pretty fun, right?